go ahead and welcome our next speaker here.
Hi.
Hello, Jonas. Thank you for joining us. Jonas Spieler from Ebenbuild. So he's going to go ahead and share his screen. And go ahead and begin when you're ready.
All right. Can you all see my screen? Okay. All right. My name is Jonas. I'm the co-founder and CTO of Ebenbuild, and today I'm going to talk about high-fidelity digital twins of the human lungs. We're now 3 years into this pandemic, and by now everybody knows that breathing through an FFP2 mask is uncomfortable and hard. Now imagine this level of discomfort, but multiplied by 1 million. And this gives you a glimpse of what it feels like to suffer from something called acute respiratory distress syndrome, or ARDS in short. In 2020 alone, 8 million people suffered from ARDS and 3 million died. Of the surviving 2 million have to live with chronic disabilities. And ARDS can hit any one of us because there are so many causes for it. At the moment, COVID-19 is quite prominent, but there's also inadequate mechanical ventilation, which is tragic because every patient suffering from ARDS requires mechanical ventilation to survive. And this is really the core of the problem, because currently doctors cannot see what happens inside the lungs during mechanical ventilation. It's a complete black box to them. And this is what we are going to change with our simulation technology. Ebenbuild opens up that black box and provides information from deep inside the lung for the very first time, allowing doctors to adjust their treatment to information never seen before. Our goal is to enrich the medical gold standard, which currently is based on diagnosis using an oxygenation index and medical image data like CT or X-ray. And then the doctors apply protective ventilation, which is based on relatively loose statistical guidelines and boils down to a surprising amount of trial and error, as well as proning the patient in the ICU. And we think that we can improve this process using high-fidelity simulation models of the human lungs. And today, I want to share with you not only what's coming, but where we are coming from and how we want to bring this technology from research to the ICU. So what you see here is essentially a couple of pictures from publication from 5 years ago by my co-founder, Professor Wolfgang Well, who has been doing research on high-fidelity lung models for a very long time. And this is the first time where they actually could show that the physics-based simulation model of the patient really replicates the behavior of the actual patient's lung within the ICU. And we could show in this paper that you really can match the global behavior of the lung as well as the regional local behavior, predicting mechanical strains and stresses within the lung. And at the time, that process from building the model based on medical images to calibrating the model, conducting the simulation and providing results took roughly 2 to 3 months. However, this was really for us a key point in time because we realized there's really the potential to bring this into clinics worldwide because there's such a huge potential for this technology. And essentially, we had 2 problems So the first is that this process took way too long to build a sustainable business around this. And the second was, as many of you might know, that the simulation interface looked something like this, right? So terminal-based UI, and this is something clearly that's not usable by doctors. So we looked into what's their industry, and this is equally unappealing for the high stress scenario in the ICU or in the hospital in general. So we really needed to solve two problems. One is the time it took to build and run the model, and the second one is that we really need to integrate this into the hospital workflow to make this technology scalable and applicable in the hospitals. And what we are envisioning is a process that looks something like this. So we have been recently working with Philips to create a mock-up of how this looks like in their bedside monitors in the ICU. So you would have a screen where you could see all your patients, and then when you see that the state of a patient deteriorates, you could push a button and push all the data needed for the creation of the physics-based model into the cloud, where we would effectively process the image data and then create the physics-based model, which you could then use to really test and evaluate different ventilation settings and then present the results effectively in the ICU at bedside at the screen that the doctor uses to monitor the patients anyway, essentially abstracting away all the technical details that are typically required for a simulation. This technology will lead to better performance of the doctors because they have, for the very first time, information from deep inside the lung. This means that patients will recover faster and more frequently. And with this, we will be able to tackle the #1 cost driver in the ICUs, that is mechanical ventilation. Now, in order to pull this off, we heavily invested in automation and integration of our technology. So it's effectively the whole pipeline from image segmentation to model extraction and building over model calibration, as well as model evaluation and post-processing needs to be automated completely. And this is why we have heavily invested into deep learning-based image segmentation technologies that allow us to automatically process and evaluate CT scans to extract the shape of the lungs as well as the state of the lungs. And we build custom-made deep learning pipelines to also do this for the lobes of the lung. And we build a multitask deep learning model to allow accurate automatic segmentation of these lung lobes. The second part is data processing and model calibration. We also completely automized this process so that overall we are now able to go from beginning to end within a time frame of 20 minutes. Next part that we are now working on is integrating this service into the hospitals so that we can really have a seamless experience for all physicians. And so the way that we envision this is that we really pull all the data from the clinical IT infrastructure, push it into computers running in the cloud where we can run all the processing and simulations, and then we can push the result back to the ICU. None of this would be possible without an excellent team, and we've been very fortunate in that we could hire really the best people in the discipline. And in addition to the core team, we also built a very large network of really key opinion leaders and advisors like Charlie Taylor, founder of HeartFlow, in combination with a large network of really key opinion leaders from the leading ICUs in Germany that help us to build this technology and bring it to that hospital. I want to close by saying that this really is a foundational technology, and we really want to apply this not only to improve mechanical ventilation, but also to other diseases and other applications such as pulmonary drug delivery for digital trials, for instance. And in the long term, we're of course also looking into applying this to different organs as well. With that, I would like to thank you, and I'm hoping for questions.
Alrighty. Well, Jonas, I have good news. You have a question. Okay, so the question here is, do you have a rough timeline, a timeline that it'll be available in the hospital?
Yeah, currently we're aiming at bringing this into the hospital in 2024.
2024. Well, excellent. Okay, and then also, again, feel free to use the expo areas and the lobby areas to get in touch with Jonas. Thank you so much for your presentation today. And we're running on time, so we will go ahead and introduce our next speaker. Thank you so much, Jonas.
Bye-bye.